got audio. Yep, we got audio. So everything should be good. Let me click this out of the way and start on the class. Okay. So with this class, we really don't have a whole lot of time to lose because we're going to lose another day. For those of you who just came in, we're going to lose another day on Monday. Next Monday is a holiday, and there will be no classes on campus. So we're going to lose another day, which also means we're going to have our exam. I'm still thinking about when to schedule our exam. I'm thinking about a Monday after 2 weeks from today. Okay, that's the Monday.
That works.
That works?
We can do it.
Okay, all right. Any objections? There are always objections. Like, I don't want midterms. I don't want exams.
Yeah, can we just not have the exam?
Well, do you want your grade? If I don't give assessment, how do I know your grade?
Take home assessments?
Yep.
So that's 2 Mondays now.
Yeah, 2 weeks from today.
Okay.
Yep.
So
Okay.
26th.
Are we gonna are you gonna cancel class Wednesday by any chance?
Wednesday?
Yeah.
Why would I cancel class?
I don't know. I don't know. You have a wife maybe, I don't know.
No, if I do the practice test on Wednesday, then next Wednesday is going to be the actual test. So there's no lecture in between the practice test and the actual test, which I don't like. Because I would like you guys to take the practice test, go home, study, prepare, and then if you have any questions, we have one more lecture. I have one more lecture to answer those questions. That's the way I would prefer. So that's why I want to space it out to 2 weeks from today, so that I can talk about the practice test on this Wednesday, and then if you guys have any questions, you can bring your questions on next Wednesday, and then we'll have the actual test the Monday after that. Does that make sense? So that's kind of my line of reasoning of why I want to kind of schedule that 2 weeks from today.
It's open notes, right?
Sorry?
It's open notes.
Okay, yeah, so let me talk about the format of the exam first. I will go over that again next Wednesday, but just in case I forget. So it's going to be open book, open notes type of exam. The exam questions are all going to be open-ended, which means that they're not multiple choice, no true or false type of answer, no circle the answer kind of answer. They're all kind of open-ended. You can bring a calculator with you, like a regular, typical scientific calculator, but there won't be any cell phone or tablet or laptop computer during the test. Okay? So in other words, your electronic device can only be there to help you do calculations. Now, if you have one of those calculators that can do binary numbers and base conversion, it's okay, not a problem. Okay? As long as your calculator cannot run Logisim, I think we're going to be okay. Or have a PDF reader or something like that. Okay?
Don't underestimate my abilities. No, I'm kidding.
And then, so you can bring anything that is either handwritten or printed prior to the test, anything at all. Okay, so that will range from the typical module thing. If you want to print out the module and bring it with you, that's fine. If you want to bring your own notes, that's fine. If you want to study together, come up with notes to bring, as long as each one of you has a copy and you don't need to share during the exam, that's fine as well. You can go to the library and check out some books, okay? And you say, okay, I find these 20 books that seem to be useful. You can bring those too. And for those of you who want to bring Holy Scripture of any kind, that's okay with me as well. I'm not sure whether that's going to help or not, okay? I'm not here to say that, okay? But if you think that might help, that's cool with me. Any questions about, how open it is when I say open book and open notes?
There's nothing electronic.
As long as physically the classroom you have enough space around you to accommodate that. Yep.
You mentioned a practice test?
Yes, practice test is this Wednesday, sorry. So on Wednesday, like 48 hours from now, we'll have the practice test, which is based on actual tests in the past. So I'll go over those questions. I'll go over the answer, so that you guys know, what kind of question I may ask based on past experience. Yep.
Is this like a handout we can take home and practice with?
Yeah, I'm gonna give you guys the URL to the past exam. I mean, it's no secret. For those of you who are slightly more adventurous, you can even go back to YouTube, figure out about the same time frame last semester, or last 2 semesters, last three semesters. I got recording all the way back to 2012 or so. So we got like 4 or 5 years easily, like 9 semesters worth of past tests. So if you want to go all the way back and study those, that's fine with me too. But I'll give you the most recent, 1 or 2 exams to give you the exposure of what kind of question I asked in the previous 2 semesters. Yep.
When you say can physically fit around this, do you mean like can fit on this table, or can just don't bring the entire World Atlas Dictionary with it?
Well, we only have like 1 desk that's kind of like standalone that has a lot of space. As long as not everybody does that, you can have 2 desks, kind of pull together. Typically, if you bring too much stuff, it's going to work against you.
Yeah.
Because you have too much stuff to dig through to find something that's useful. So my recommendation is to condense all the notes, condense everything to just, I would say, this is just me, okay? I would condense it to maybe about 10 pages of stuff, okay? With the other stuff as a backup, okay? So you have everything else in the bag or somewhere else. But you don't want to have to dig through all of that stuff all the time, okay? Yep.
How much time are we going to be given?
The whole class period. So we got all 80 minutes, not including the lab.
Oh, so it's just a lecture.
Just the lecture.
Will there still be a lab that day?
I have not decided yet, like most things.
You said it was next Wednesday?
No.
This
It is-
Wednesday is the practice.
This Wednesday is the practice test. There's no class next Monday. So next Wednesday you can bring your questions. If you study and go okay, I'm not really quite sure what this means or how to do this or what that thing is, bring those questions next Wednesday. And then the actual exam is the Monday after that.
Okay.
Yep.
Will we be expected to do a proof?
No.
Okay.
So no proofs in this class, but I do expect you guys to understand the concept, what is a look-ahead adder? Why does it work? Or how does it work? How fast is it compared to the alternative implementations? Okay, so I do expect you guys to be able to do that. I can give you a schematic in LogicSim in the exam. I can take a screenshot and say, okay, look at these gates. Okay, what does it do? If I present these things as inputs, what is going to be the output? Or if this is the output, this is partially input. This is a part of the input. What is that missing input? What kind of value can it be to give me this kind of output? So I do fully expect you guys to understand how the gates work, okay? Especially in the context of an adder and a subtractor.
We have to memorize exactly the difference between an OR and an XOR, or will there be little notation that gives us
That would be your responsibility.
Okay.
So if you want to bring a key, with the shapes of all the gates that we have used in this class and also the lab, you can bring that with you. So I'm not going to be responsible to give you guys material that we have already introduced in class in the exam.
Okay.
If you want to have a table to remind you, okay, what is the result versus the carry versus the borrow and stuff like that, bring that with you. Okay, if you think that you may not remember the overflow flag and how it is computed as a logic gate, bring that with you because it's part of the notes. Okay. If you take a look at the videos, okay, and you say, oh, there's one screenshot that is useful because I use my tablet to write something. Well, freeze that frame, cut it out, print it out. I mean, you don't even have to translate it and put it in your own words. I mean, just copy and paste. So is that okay? But there's no watching of YouTube during the exam.
Dang it.
Unless it's for entertainment. No.
I gotta watch my Let's Plays.
No. Just no YouTube at all because somebody's going to say, but I find your lecture entertaining. Can I watch that during the exam? No.
Psyche about.
So is that okay? I mean, do you guys understand, what kind of open-ended it is? But that's also putting responsibilities on you to bring along the material that you might find useful. Okay, so I'm not going to answer questions like, oh, can you remind me what is the equation for the overflow flag during the exam? I'm not going to answer those questions. Is that okay? All right?
How many points was it?
I have not
Practice
decided yet.
Okay.
It'll be enough questions.
Large fraction of your grade.
Yeah.
Oh, you mean what kind of percentage?
Yeah.
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 Well, that's in the syllabus.
Oh, okay. I mean, like that.
You can bring the syllabus with you too. 20% of your final grade comes from exam 1.
The practice one?
The practice exam does not carry any weight at all. Okay, all right. Any other questions? No other questions. Yep, go ahead.
What if you ace the practice and like fail the real exam? Just take like an average or something?
I may feel sorry then. But that's a big may as well. I'll decide when it gets that way.
Wait.
Yep.
So the practice we're going to be taking here.
The
it's not
practice is
take-home
just
thing.
me giving you guys a look at the questions. So, one thing I can also do is I can give you the questions ahead of time. But anyway, it's just going to be questions from the past, and I'll talk about the solution to those questions.
Oh, okay. When you say ahead of time, it's not the questions from the test, it's the questions from the practice test, right?
Yes,
Okay.
because I have no idea what I'm going to ask this semester yet.
Alright.
I usually make up my mind like maybe a day before the actual exam. But you can be guaranteed, almost guaranteed, that it's not going to be the same as last semester's.
Same subject, hopefully.
Yeah, same stuff, but asked differently.
How many sodium ions are required to read?
Okay, so are there any further questions about the exam, the first exam? Okay, well, yep.
I missed this if you were talking about it. What day is it?
2 weeks from today.
All right.
Yep. All right, so let's move on and we'll start to talk about floating point numbers today. As I said a little bit earlier, we have quite a bit to catch up with, especially because we're going to lose another day. Okay, so floating point representation is kind of an interesting topic because at this point we have talked about several things, right? We have talked about the unsigned representation, which is the plain, simple way of looking at binary numbers and say, okay, what can this binary number be represented? What is the value represented by these zeros and ones? So the first thing we introduced was basically unsigned number. Okay, so we start with the least significant bit telling us how many ones we have. The next one tells us how many twos, and then fours, and then eights, and then 16s, and so on. And you add up all of those things that has ones, and that's the value represented by a binary number. And then we talked about the signed representation. We talked about how we can use 2's complement. So using a number wheel, we basically allocate 1/2 of the wheel on negative values, while the other half, just maintain what they usually represent, which are the non-negative values. Is that okay? Do you guys remember all that stuff? Hopefully. Okay. So now the question is, then how do we represent pi? How do we represent things that are not integers? Okay. So that's going to be the focus of today's lecture, as well as the lab. So the module that I'll be reading, well, not reading, but I'll be using is going to be floating point number representation. And I'm hoping most of you has an opportunity to read ahead of me, at least to kind of get an idea of what it is about, what kind of math are we going to be dealing with, and that sort of thing. All right, so let's go ahead. Let me turn on my tablet so that I can give you some examples first. Okay. I need my pen. So we'll do a base conversion first, okay? But before we do that base conversion, we'll kind of go back to some really boring topic like, how values are represented by numbers. And this time we'll go ahead and try this number here, 97.625. Okay. It's a base 10 number. If I don't emphasize, it is just base 10. So quite obviously, as a base 10 number, we all know what value it is representing. It has 9 tens, 7 ones. What about the 6? What kind of unit are we talking about? What is the 6 telling us?
6 tenths.
6 tenths. Very good. And 2 hundredths and 5 thousandths. Okay, very good. Okay, so we know what this number is representing in base 10. So now I want you to represent the same value, but in base 2. How are we going to do that? All right, so we'll just use the usual approach. Okay, so in other words, this is the currency. Okay, so this is the amount that I want to give someone using the least number of bills and coins, except we're dealing with base 2 stuff. In other words, your currencies will come in 256, 128, 64, 32, 16, 8, 4, 2, 1. What about the other side? 1/2, and then a quarter, and let's stop at the 8. Okay. So what are we gonna do? So we'll start with 128 first. Do we have any 128? Nope. What about 64s? We got one of those. Okay, so once you take the 64 out, what is the remaining portion? 33, right? Okay. 33. Okay, so when we move down to 30 to 32, which is a power of 2, we got one of those too. So we only got 1.625 left. So when we get to 16, none of those. Get to 8, none of those. Get to 4, none of those. Get to 2, none of those. Get to 1, and we got one of those too. So now we only have the fractional part left, which is the 0.625. Is that making any sense? So it's okay. We can deal with that as well, okay? Because now we can ask, how many halves do we have? We got 1. After that, we got 0.125, which is 1/8, right? So when we ask the question of, do we have a quarter? The answer is no, we do not need a quarter, okay? And then when we ask the question, do we have any eighths? Then the answer is yes, we got 1. So are we still doing okay so far in terms of coming up with these values? 164, 132, 1, 1/2, and 1/8. Okay? And this can be done without division at all. It's just comparison. You're really just comparing how much is left over with a power of 2, because in the case of base 2, you can either have 0 or 1 of each power of 2. So there's no division involved. Okay. What kind of number are we dealing with here? If you tilt your head clockwise 90 degrees, you have the binary number. Where's the point? The point is always here. It is separating the unit of 1 versus the fractional unit. But do you see how this representation is no different from base 10? Okay? Except it's easier. It's longer, but the math is actually easier in many ways. Okay. So now that we understand, we can have decimal numbers, binary point numbers, just like we can have decimal numbers in base 10. What about the rest? Well, the rest is about the representation. Okay, so even though we can look at this number and go like, there's a binary point right here separating the number of 2 to the power of 0 from the number of 2 to the power of -1. When you represent the number as just a binary bit pattern, there's no way you can actually put a point somewhere. Okay, it cannot be represented by transistors or gates. So you have 2 ways to proceed. One is you make an assumption. Okay, so let's say you're dealing with 32-bit numbers, and you're just going to assume that point to be between 2 particular bits. Whenever you do calculation, you just make the assumption that you have that point, being somewhere. Okay, the alternative of looking at that is also just that you instead of representing how many, if you look at the binary number, instead of looking at the binary number as the number of ones, you're just looking at the number of some negative powers of 2. I'll give you an example. If you look at this amount here, if I know the smallest denomination is an eighth of a dollar, one way to solve the problem really quickly and easily is not to represent the number of dollars, which would require fractions. Instead, I'm going to represent the number of eighth dollars. Then it's always going to be an integer. Is that making any sense?
Yeah.
It's just like go ahead.
Shift over the decimal point and then just say where the decimal point is going to go.
Yep, exactly. It's just like in terms of the currency, instead of representing the number of dollars, I can always just represent the number of pennies. Then I don't have to deal with fractions either. Is that okay? So that method is called fixed point representation, where the binary point is always between 2 particular bits, but you have to remember which 2 bits, and it's going to be the same, throughout all the program, the entire program. Okay. What is the problem with that approach?
It's very limited.
It's very limited. Limited in terms of
Scope of what numbers you want to use.
the range of values. Very good. Okay, so you didn't quite use that word, but I think that's what you meant. The range of values is limited. Okay. Why do you want to have to deal with a large range of values? Especially when you think about the original applications of some of the earliest computers. Some of the earliest computers were used to compute the trajectory of projectiles. So in that case, what kind of range of values do you need? Or if you fast forward to today, what do we use computers for?
Everything.
Everything. But what about the Department of Energy, the DOE? Like in the Lawrence Livermore Lab. Okay, what do they use those supercomputers for? Particle simulation. Okay, particle simulation or subatomic particle simulation and stuff like that. Because you don't want to have to build an accelerator that is going to cost like tens of billions of dollars, unless theoretically you can say yes, we think this kind of particle exists in simulation. And what kind of mass are we talking about when you're talking about subatomic particles?
Like micrometers, smaller than a ton.
Very, very, very small.
Yeah.
But in order for the experiments to confirm the existence of certain types of particles, how fast do you have to accelerate the particles to?
Very, very, very near the speed of light.
Near the speed of light, very good, which is a pretty big number, right? So we have to deal with tiny little values like the mass of subatomic particles, but at the same time we also have to deal with large values like the speed of light, or the amount of energy it's going to store, that sort of thing. Okay, so how do we deal with that? How do you deal with that with a calculator? Because I'm pretty sure for those of you who have taken physics, you have to enter fairly large numbers sometimes, and you have to enter fairly small numbers sometimes. So do you have to enter like 0.00000000000 and then some number, or append a bunch of zeros to the right hand side because you're trying to deal with a large value? Scientific notation. Okay, so are we all comfortable with the concept of scientific notation in base 10? Not in base 2, just base 10. Okay, so what I'm going to do is I'm just going to introduce the whole notion of scientific notation. So scientific notation looks like this. Okay, this is not a normalized scientific notation, and okay, so we'll just take a look at this number here. What is the value represented by this scientific notation specified in base 10? This number here, the one that I just wrote. What is the value of this thing?
21 10 to the power of 16.
Yeah.
So it's 21.65, which is called the mantissa, times 10 to the power of 16. This 16 is indicating the magnitude which is in terms of 10 to the power of that number. Okay? So the other part, which is called the mantissa, is really the multiplier to that unit, which is a power of 10. Is that okay? So I'm choosing this representation using the e, lowercase e, to separate the mantissa from the exponent, because that is also how you specify scientific notation in C and C++. Okay? So do we have any questions about this? Now in the lab today, there will be a question kind of like this. Okay, I'll give you the scientific notation, and you have to answer, a particular question about it. If you don't know how to use your calculator to use scientific notation, you might want to find the manual first. You can find it online, okay? Because some scientific calculators do not use the E key to enter the exponent. E is actually exponent to the natural E, the log number. Okay, so you have to look at your own calculator to find out how to enter the exponent of 10. Some calculators uses the key which has EXP written on it. Okay, but it depends on your calculator.
Some use double capital E.
Is it double capital? Okay.
Yeah, some.
So it depends on your own calculator. Whatever you do, lowercase e usually is not. Okay, scientific notation, it is actually the constant e to the power of something. Is that okay? All right. Okay. So now we want to look at this as a binary number. Okay, this is base 10, right? So the question is, can we borrow this idea of a mantissa followed by some power, and you only specify the power, but use it in base 2? Is that okay? All right. And we have a very handy example right here. Let's try to use that example and see if we can use it to illustrate, how to use base 2 scientific, not scientific notation. It's called floating point number, but same thing as a scientific notation. So let me write this number the usual way, and this is 1, 1 followed by 4 zeros, 1 and then 0.101. Okay, in base 2. All right. So my first question is, if I say this, would anyone argue and object and say, Tack, you just changed the value of that number? Nope. Times 1 doesn't do a single thing, right? Okay. What about this? What if I move this binary point? I don't want to call it a decimal point anymore because this is a binary number. So what if I move this binary point over here? So I'm changing the mantissa. So it is 0.1101 in base 2. I mean, obviously the mantissa is no longer representing what it used to be, right? If you just look at the mantissa, how does it compare to what it used to be?
Well, you forgot a zero.
Oh, I forgot a 0?
No, I mean times 1 0.
Oh, okay, I forgot a 0 there. Okay. There we go. Okay, so now I just moved the point, right? I moved the point from here to here. If you just look at the mantissa, how much has it changed, the value? Now you can look at the actual subtraction, but what I'm really interested in is the ratio of the value, before and after. What did I do to it?
Times 1 0.
Hmm?
Would it be times 1 0?
Times 1 0. Times 1 0 in base 2, right?
110.
It is actually divided by 1 0 in base 2. It is now 1/2 of what it used to be. Is that okay?
Yeah, because it's base 2, not base
Because it's base 2. Okay, so one quick way to look at this is to look at it this way. What used to be specifying an 1/8 is now specifying a 16th. What used to be specifying a 1/4 is now specifying an 1/8. So if you look at every single digit, okay, each one is only representing the quantity of 1/2 of what it used to be. Is that okay? So can we agree that on the second line, the mantissa is only half of what it used to be? Is that okay? All right? Yep.
They did the same operation in like base 5. Would it be 1/5 what it used to be?
Yep, exactly. Whatever base you use when you shift the point, then it is representing either that a multiplier or divider, based on which way you shift the point. Okay? So if I were to put a 2 here, would that be okay?
Yeah.
Okay. So now I can do the same thing again and again and again. Okay, 1, 2, 3, 4, 1, 1, 0, 1 in base 2. Would that be okay? All right. So I can keep doing this until I have 1 point and then blah, 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 blah. Okay? So let's just go all the way, and then we say this is 1.100000, 4 zeros, 1101. And what kind of power of 2 are we going to be dealing with? Let's not deal with.
64.
Let's do it this way. Specify the power of 2.
6, I think.
So we have 0. This is the original. I call it 0. 1, 2, 3, 4, 5, 6. Is that making sense at all? I have not changed the value. I have simply changed the representation. Okay? But what is important here is the last line. Okay, let me point out which line we are talking about here. This line here is representing a mantissa that is quote unquote normalized, because I like my mantissa to be between 1 and almost 2. Just like in base 10, you want your mantissa usually to be between 1 and almost 10. Is that making any sense? Okay. So now, if I really just want to be binary, I can instead of writing the 6 here, I can say 1, 1, 0 in base 2, because that's actually the same thing. So if I choose to represent a number this way, I need to represent the mantissa, okay, using some bits, and I have to represent the exponent using some bits. And of course, if I need to deal with negative values and so on and so forth, then the sign will also be another bit, okay, because the sign cannot be absorbed by one of these bits. Is that okay?
Wouldn't the 2 be 1, 0 as well?
Sorry?
Wouldn't the 2 also be 1, 0?
Well, the 2 is not really a part of the number. I'm only representing the exponent itself and also the mantissa itself. All right, so if this is okay, then we're going to kind of go into the notes itself, because I want to point out where all of this stuff is located. So I have a module called floating point number representation. And in here, one of the first thing it does have is a hyperlink. So if my module has a hyperlink, what are you going to do with it? You just kind of ignore it, right? It's like some strange text here has a slightly different color and underline. I don't know what it is, but I'm going to ignore that. So, assuming you're curious, okay, you're going to right-click on it, and it goes to the Wikipedia page on double precision floating point format. The reason why I bring you here is because there's a graphical representation that you might find actually quite useful, okay? So in this graphical representation, just ignore everything else, okay? We have bit 0 all the way to the right-hand side, and then we have bit 63 all the way to the left-hand side. But this time, I'm not looking at a 63-bit signed or unsigned integer, because it is just a concatenation of parts, okay? So now the question is, what are these parts? What do they do? How do they influence the value represented by these 64 bits? So we're doing okay so far with the concept of, we're just putting a bunch of bits together, and altogether there are 64 bits. Bit 63 is also known as the sign bit. That's the easiest. If it is a 1, then the rest is representing a negative value. If it is a 0, then the rest is representing a non-negative value. It really is just sign, Okay, if it's a 1, then we're dealing with negative. Okay, so we get the sign bit out of the way. So now we're dealing with the green part. The green part is known as the exponent, which has 11 bits. So the green part starts from bit 52 and it ends with bit 62. All right? So the way you look at this is you look at the green part as a 11-bit unsigned integer. So the way you interpret the value is this is telling you the number of 1s, 2s, 4s, 8, 16, and so on. And then you just add up all the ones that have a 1 corresponding to it. So that's basically how we are dealing with the exponent. But then you ask, but then the exponent can only be non-negative because it is an unsigned interpretation. Well, as it turns out, the green part, if you look at just the unsigned interpretation, in the Wikipedia page, it is called lowercase e, which is awfully confusing, but they call it lowercase e. Lowercase e can range from 0 all the way up to what? If you have 11 bits and they're all 1s, what is the value represented by that? 2047. Okay? So e, lowercase e, can go from 0 to 2047. So the actual exponent that you want to apply to 2, the power of 2 that you're dealing with, is biased. In other words, you take whatever e has, which is the green portion, interpret it unsigned, and then you subtract 1023 from it. Whatever that difference is, which can potentially be negative, is the actual power of 2 that specifies the magnitude. Is that okay? Okay. All right. Then what about the rest of the bits? It's called fraction. It's not called mantissa. Why? So you can see there are 2 representations, but of the same thing. You can see the first one here, it is 1 point, okay? So 1 point is always there, it is not one of the bits. And then bit 51, which is the most significant bit of the pink portion, is specifying the halves. Bit 50 is specifying the quarters, and so on, of the mantissa. What about the 1 itself? It is not represented at all. It is not a part of the salmon or the pink color portion. It is always going to be there. Because if you think about a normalized base 10 number, the leading digit can go from 1 to 9, right? Because we're dealing with base 10 numbers. But if you're dealing with base 2 number, it cannot be 0. What is the only digit other than 0?
1.
It's 1. So that's why the 1 is always there. It's constantly there. And that's why it is also not represented. It's always going to be there. And that's also why the pink portion is called a fraction. It is the fraction of the mantissa. Are we still doing okay so far with this notation? Okay? So the value represented by something like this can be, we can use this interpretation. We can also use the other interpretation, either one is fine. Okay, because this one, the second one, is using a sigma notation to look at each bit and say what kind of power of 2 is it representing. That's the only difference between the top one versus the bottom one. This one uses the sigma notation to spell out the value. The other one is kind of using a notation to say, oh, bit 51 is the first digit to the right of the binary point. B50 is 2 digits from the binary point, and so on. But other than that, they represent exactly the same thing. Do we have any questions at this point about a double precision floating point number? How the bits are utilized? No questions? All right. Well, if there are no questions, then we can dismiss the class and you guys can start with your lab.
All right.
No, not really. I'll give you some examples. Okay, so I'm going to give you some examples, and then we'll do 2 things. One is we have a known value to represent. How do we figure out the actual bit pattern for that particular value. So that's one thing we can do. The second one is I will give you a binary representation. We'll try to figure out what value it is representing. So we'll go in both directions. Okay? All right. So let's go ahead and reuse the same value that we had before, which is this value here. Okay? What we know in base 10 as 97.625, or what we also know as a scientific notation in binary as 1.1000001101 with a 6 as the exponent. How do we represent this as a double precision floating point number? That's going to be our first task. Okay? All right. So let's go ahead and work this out. So the nice part is I got most of the work done already. The mantissa is already normalized. It is already in the form of 1 point blah, 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 blah. So the conversion process is mostly done. So now we want to look at the sign bit. What do you think is going to be the sign bit of this double? 0, because the value is non-negative. Okay, so we'll put a 0 here. What about the next 11 bits? What is the value of the next 11 bits? It's not 6, because remember it is biased by 1023. So if the actual power of 2 that you want is 6, you have to add the bias amount to it. And the bias amount is 1023. So what is 1023 plus 6? 1029. So how do I represent 1029? Okay, first of all, 1024 is 1 followed by 10 zeros. Okay, so we're going to say, okay, here's 1, and then we'll specify this is bit 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. So once I have 1024 and I subtract that from 1029, what do we have left?
Where did you get the 6 from?
Huh?
You
The
said
6?
you subtracted the 6.
Yeah, the 6 is from here.
Oh, the power, okay.
The power of
I
2
gotcha.
as a magnitude.
Gotcha.
Okay. So I have 1023 plus 6, which is 1029, right? And then that one here, the one at bit 10 is going to take care of 1024. How much do I have left? 5, right? No. Okay, I think we got 5 left. And 5 is 1 plus 4, right? So we're going to have 1 here, because 1 is 2 to the power of 0. 4 is 2 to the power of 2, so we have another 1 here. The rest are all zeros. So we'll just fill in the rest with zeros, like so. Okay. So now we got 12 bits figured out within the 64. What about the rest? What do you think is going to be the next digit or the next bit? Right here. What should go there? We only need to represent the fractional part of the mantissa, not the entire mantissa. So what should go there? This goes here, this goes to the next digit, and so on. So I'm going to specify all that stuff. So it's going to be 1 followed by 4 zeros, 1, 1, 0, 1, and then a whole bunch more zeros. Okay, I'm not going to write 40 something zeros here. I'm just going to use dot to mean the rest are all zeros. Is that okay? So let me just emphasize what I have just copied. This portion goes here. Okay, and the key is this is everything to the right-hand side of the binary point of the mantissa. The 1 to the left-hand side is not a part of the double precision floating point number. It is not represented. So is that okay? How do we test this theory? I mean, after all, this is a theory. I'm saying that this 64-bit pattern is going to specify the value of 97.625 interpreted as a double precision floating point number, but I can claim anything I want in this class. So if I start to claim something like this, and you look at this and go like, I'm not so sure. I mean, if you are really sure, you're not going to be in this class. So what do you do to test my theory? How do you test this theory? Well, we're going to write a small program, okay? And then we'll test it. Is that okay? All right, so we'll go ahead and switch to a terminal. Switch to a terminal that is large enough. Is that large enough? Yep, this is the good one. And we'll just call that test.c, okay, for the lack of a better name. The first thing I'm going to include is stdint.h. It's called standard integer.h, which defines the uint64_t. It makes sure that I can actually say, okay, this integer has exactly 64-bit, because the width of integers is actually important here. Okay. Main is just a regular int, and I don't even want to force it to 64 or 32-bit because that depends on the compiler. I have one single variable, uint64_t. We'll call it x here. I would initialize x to 0, and I'm going to have x equals to x plus x, which obviously doesn't do a single thing, but I need this so that the compiler doesn't complain. If I don't have this, if I don't have these two lines, the compiler will optimize x out of existence, which I need for testing the program, testing my theory. If I don't have the second line, the compiler will give me a quote-unquote warning to say that x is initialized but not used. It never appears on the right-hand side of any assignment. It's never used. So all of this is just to make the compiler quiet and say, okay, we know what we are doing, so don't complain. This is my entire program. Does it look like this program is going to test my theory? No. But we're going to go with it. So we say gcc-g, which means we want to include debug information, because we're going to use GDB. Okay? That's the whole thing. Okay? GDB is my tool of doing all of this stuff. -wall, which represents warn all. Okay? I want all the warnings possible. And then we can just go ahead and say -o. This specifies the executable name, the name of the executable file, and then test.c is my source file. Okay, compiles just fine, gdb test. So we are now in the debugger. I will put a breakpoint on line 9. It doesn't really matter whether I put the breakpoint on 7, 8, or 9. Okay, anywhere in the program is fine. Run the program. Print x, not surprisingly, it is 0. Okay. Now I want to specify the bit pattern that we have just figured out into x. How do we do that? Okay, so we are looking at this particular bit pattern, and I want to stick this bit pattern into x. So how do we do that? First of all, in C and C++, there's no binary representation. And two, even if it does, I don't want to use binary, because that I will have to enter like 64 digits, which is cumbersome.
Plug in 97.625.
That won't work, because that is going to cast it. So the debugger and C knows how to cast double precision floating point numbers, and it will just do a rounded version of that. In other words, it will store 98 as an integer into the unsigned, which is not what I want to do. What I want to do. So what I'll do instead is I'm going to do a base conversion to base 16. Have we talked about base 16 in this class?
Yes.
Okay. So to do base 16 conversion, we group the digits in groups of 4, because every 4 bits is one base 16 digit. Why do you think that is the case? Because 2 to the power of 4 is 16. So every 4 bits is one base 16 digit. Is that okay? So that's why I'm grouping these in groups of 4. So now I'll do my conversion. This is 4, 0, 5, 8, 6, 8, and then a bunch of zeros. So my hexadecimal or base 16 number is going to be 405868, and then a bunch of zeros. How many zeros are we dealing with? In other words, if I want to fill up 64 bits with base 16 digits, how many digits am I talking about? 16 digits. So I have specified how many here. 1, 2, 3, 4, 5, 6. So I got 10 more zeros to pad to the right-hand side. Is that okay? All right. So I'm going to keep this part visible so that when I use GDB, I can still keep an eye on it. So we say set var. This is a GDB command. X equals 2. GDB knows the name of the variables in the program, so I can just do this. So now we just have to specify 0x, which is the prefix of a base 16 number, and then we just enter the number. 4058 6 8, and then a whole bunch of zeros, and I said 10 of those, right? 1 2 3 4 5. 1 2 3 4 5. Okay. Press the enter key, and we say print x. That doesn't look like 97.75 of 625 to me. Maybe this will do it. That just gives us back the hexadecimal representation. That's not 97.625. So how do we look at the very same 64-bit, which is currently interpreted as an unsigned integer? How do we trick GDB or the compiler to look at the very same 64-bit and say, oh, we want to look at this as a double precision floating point number? Casting won't do it. Okay, let me just show you what casting is going to do. So casting is just that, right? It's not doing it. That's because casting is based on the value. Okay, it's casting the value itself, which is a huge number, and into a double precision floating point number. So that's not going to do it. Let's try this. Okay, I'm going to have a print here again, and this time I work on this step by step. So there will be a lot of back and forth. So the first thing is, okay, I know I have to start with x, but I'm not just looking at x itself. The value of x as an unsigned 64-bit number is totally useless to me. But the address is useful. So I'm going to extract the address of that. So you're looking at ampersand x here. What is the type of ampersand x? It's a pointer to a 64-bit unsigned number, right? Once you have a address, you can now cast it. You can cast it from the address of a 64-bit number to the address of a 64-bit double precision floating point number. Okay, let me show you exactly what I mean by that. So I'm casting the address of x into a pointer or the address of a double. I'm looking at the very same 8 bytes in memory, the very same 64 bits, except I just say, it's not, these 8 bytes are no longer unsigned integers, okay, or parts of an unsigned integer. These 8 bytes are now specifying a double precision floating point number. But nonetheless, at this point, I only have the address. So the last thing we need to do is to say, let's not look at the address, which is just going to be some memory location. Let's dereference it. What is dereferencing? You're given a pointer or an address, and then what do you do?
Looking at whatever's stored in the address.
Right, exactly. So we are looking at the very same byte, the same 8 bytes or 64 bits, stored at that location. But the interpretation is now different because this dereference, this asterisk here, this dereference here, is going to look at the very same 8 bytes, but this time it would interpret it based on the double pointer type. Is that okay? Now, the C class, which is a prerequisite of this class, really should include the discussion of typecasting, pointers, dereferencing, and stuff like that. But you may not have seen anything like this, of how things are combined. Okay. Well, first of all, we just want to get our 97.625 back. So let's see if that is going to work. Woohoo! But do you guys understand the mechanism of how this works? Sort of? Okay. So the key is not to cast the value, because that would never work. You have to cast the address of the variable and say, oh, don't look at this as the address of an unsigned 64-bit number. Look at this as the address of a double precision floating point number. Now tell me what is there. That works. Is that okay? All right. But, we got our 97.625 back. So are we okay with the process? Starting with a particular value, how to convert it into a double precision floating point number format, bit by bit. Is that okay? More or less? Okay. So the next thing we're going to do is I'm going to give you a bit pattern, and then we'll try to figure out what value is represented by that particular bit pattern when interpreted as a double precision floating point number. Is that okay? All right. So we'll go ahead and take a look at a pattern. I'm not going to give you guys something that's really, really hard to convert. So this is bit 63. Let's start with the 1 here. And then we'll have just 1 followed by 10 zeros. 5, 6, 7, 8, 9, 10. And then we'll specify just 1, 1, and then a whole bunch of zeros after that. Okay, so let me just point out this part here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This portion is E, and then this portion here is the fraction of the mantissa. Is that okay? All right, so we'll take this apart step by step. The sign bit is a 1, which means the value it is representing is negative. Okay, so we'll just say that implies the number is negative. Cool. E itself is pretty easy to figure out, because E is just 1 followed by 10 zeros. So the value of E as an unsigned number is 2 to the power of 10, which is 1024. Okay, so E is 1024, but the actual exponent of 2 is not E. Remember, it's biased. By how much? By 1023. So the actual magnitude we are dealing with is 1024, which is E, minus 1023. So our magnitude is just 2. Is that okay? 2 to the power of 1, which is 2. All right. What about our mantissa? Our mantissa always starts with a 1 point, right? But whatever is to the right-hand side of the point is represented explicitly in the number. So we are dealing with 1, 1, and then followed by all zeros here as a base 2 number. Okay, so we are dealing with a base 2 number here. So I want to figure out what is the mantissa itself. What is the value of the mantissa itself? What do you think it is? The 1 is easy. The 1 to the left-hand side of the binary point is really just 1, because it is 1 times 2 to the power of 0, which is 1. So the next one is the half, and then the one after that is the quarter. So we got a half, we got a quarter, which means it is 0.75. Add that to the 1 itself, we have 1.75. So the mantissa
where's the third one?
is 1 plus 0.5 plus 0.25. The 1 comes from here, the half comes from here, and then the quarter comes from here.
I was confusing.
And the reason why we know that the first one is actually a 1 is because our magnitude became 2 to the 1, right?
No.
Oh.
No, that 1 point is always there. It is implied. It's never stored. That 1 is never stored, always implied.
Okay.
Okay? Okay, yep.
So what if you just have like a decimal? Like what if there's no 1 at all, if it's just like...
You have to normalize it before you can store it.
Okay.
So you have to shift it until the format of the mantissa is 1 point something.
Okay.
Then you store just the fraction part of
Like
the
the
mantissa.
scientific notation. Okay, gotcha.
Which leads us to a problem, but we'll talk about that problem later. Okay? So that turns out to be in base 10, 1.75, but because the value is the sign, which is negative, times 1.75 times 2, the 2 comes from the magnitude of the exponent, right? So that turns out to be what? Negative 3.5, I think? Unless my math is really, really bad. Is that okay?
That's where the 2 to the 1 comes into play. Is that 2 from the 2 to the 1?
Yes.
Okay.
Yeah, 2 is basically 2 to the power of 1. So that's coming from here. That goes here. And then the sign determines whether the number is negative or not. Is that okay? Looks like a football play. I think this is easier. Okay, so my claim is the binary bit pattern that we specified at the top of your screen specifies the value of negative 3.5 when interpreted as a double precision floating point number. So how do we check that?
C.
The C program. In fact, we don't even have to do a new C program, okay? So the way we do this is we enter this particular bit pattern. Well, we can enter the bit pattern first, or we can just enter this value first. Which way do you want to do it? Do you want to enter the floating point value of negative 3.5 and look at the bit pattern to validate this whole process, or what?
We could do it that way.
Okay, let's do it that way because we haven't done it that way before. Okay, so the way to do it is to do it like this. So we're going to say set var again, set var, but this time we're going to use the same trick, but then it becomes the left value. Because we are trying to store a double precision floating point number into the space that the program thinks is a 64-bit integer. So that's why we have to pass the left-hand side of the assignment and not the right-hand side. Now, when you look at 3.5, I would just be very careful and cast negative 3.5 itself into a double. The reason why I'm casting it is because 3.5, as far as the debugger and C is concerned, may have a default type of just float, which is the 32-bit, the single precision floating point number. So the implied type may not be double. So I'm going to be extra careful and just say, no, I want the double precision floating point number version of negative 3.5, not the single precision. Because there's an off chance that you might see this as a single precision. Is that okay? All right. So we're going to press the enter key. Okay, no problem. So now when we say print /x, which means print in hexadecimal, the value of x, it will give us a bunch of hexadecimal digits. So in this case, it gives us basically C00C and then a whole bunch of zeros. Okay, let's write that down on the tablet and then double check and see whether we get our binary bit pattern back. Okay, so switch back here, and we'll scroll off the screen a little bit so that I'm not copying, right? So I'm not cheating and just copy what I had earlier. So we have C00, C, and then a whole bunch of zeros after that. That's what we saw in the GDB screen, right? Okay. So now we say C is 1100, 0 is 0000, 0 is 0000, C once again is 1, 1, 0, 0, and then a whole bunch of zeros after that. Okay, so now we can go back to what we had earlier, and is that what we got? We got 1, 1, 10 zeros, and then 1, 1, and then all zeros after that. And this time, do we have the same thing? Do we have 2 1s and then 10 zeros? So we got 2 1s, and then we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. 2 more 1s, and then all zeros after that. So this way, I can double check and say, okay, yep, I think the conversion process is correct. Do we have any questions about this part? In other words, if I give you the bit pattern, can you figure out the value represented by the bit pattern? If I give you the value, can you convert it into the binary bit pattern? No, right? Okay.
Barely.
That's okay. Barely is a very good answer. I mean, after all, I wrote all of this for a reason. Okay? All right, so what we have covered at this point is the representation itself. And the rest of this module is about the conversion process, okay? But it is described in a way that you can actually code it. The conversion process that I went through is kind of an eyeball algorithm, okay? It's based on a correct understanding of the format, but it's not very structured. Okay, if you give me a value, I can tell you what it is, and I can work my magic on just that number. But it's not code, okay? You cannot just give me any value and the same algorithm works. This module gives you the algorithm to make it work, okay? So one thing we want to do, okay, this is kind of off topic, but kind of not off topic. So what we are looking at here, okay, let me magnify a little bit. This part here is what we call a regular expression. How many people have heard of the term regular expression? Or sometimes, okay? Most of the time it's called REGEX, or regex, which is the short abbreviated version of regular expression. What is that? Do you think you might encounter regular expression as a developer, as a computer scientist, as a system administrator, perhaps?
It's a format of what you're expected to see.
Sorry? Okay, go ahead.
It's a format what you're expected to see. The kind of
it's a pattern, right? It's not telling you what, the specific value. It's not telling you I'm looking for 1.25 E6. Okay, it's describing a pattern that we're looking for. Why would that be useful? Not in assembly language programming or computer organization.
Patterns?
Huh?
For finding patterns?
For finding patterns, but why do you want to find patterns? Let's say you're dealing with a web form of something, okay? Why would you want to understand regular expression in that context?
Because you have various amount of inputs that could come from anywhere. I had to use this for like filtering out certain entries.
Validation.
Yeah.
So you need it for validating the input of some people can enter the wrong thing, and you have to say, okay, this is in the wrong format. I cannot accept this. There was another hand. Yep, go ahead.
I was just saying, I've seen in URLs, looking to match a certain URL, like a username or a date or a slug or something.
Yep. And you can find files too. You can find files of a particular pattern. So if you remember, okay, I vaguely remember I named the file with, this year and this month and then these particular words, you can use regular expression to help you search for files that can fit that particular format. Is that okay? All right, so we want to look at this and find out, okay, what exactly are we talking about here? So we have several things that are kind of important. So this is the explanation. In other words, I'm not going to read my whole explanation, so I'm just going to explain as we go. But the detail of the explanation is here already. Square brackets specify, characters that can take that place. Okay? So in this case, open square bracket plus minus close square bracket means this can be a plus or a minus. That character can be a plus or a minus, but not anything else. Okay? And then we have a backslash equal. Backslash equal is one thing. Okay? So do not look at it as backslash and equal. Backslash equal means whatever is before is optional. You can have 0 or 1 occurrence of that. Okay? So what is right before the backslash equal? The sign, right? So the sign is optional. Is that okay? So if you don't specify the plus or the minus and you start with digits, it's fine. If you specify, redundantly, specify plus blah blah blah, it's okay. If you specify negative something, that's fine too, because the sign is optional. Moving on to backslash d. Backslash d is basically representing a base 10 digit. It can be 0 all the way up to 9. But only one digit, okay? Backslash d itself is representing one base 10 digit. So this base 10 digit is always going to be there. Okay? And then we have backslash open paren and backslash close paren. That is used for grouping purposes. Okay? It's just saying, okay, whatever is enclosed by backslash open and backslash close parentheses is treated as one unit. Okay? Look at it as open curly brace and close curly brace in C programming. Okay? It's just making a block out of something. What is in that block? Backslash period is just a dot. Okay? That's because a dot has other meanings in regular expression. So backslash dot is really just the dot itself. Okay? And then we have backslash d again, which means it is a base 10 digit. And then this time we have an asterisk. Asterisk by itself means any number of whatever is right before this, including 0. So that means after the decimal point, I can have nothing else. I can have any number of base 10 digits after the decimal point. Is that okay? But the entire fractional part here, starting from the backslash open paren and ending with the backslash close paren, is followed by a backslash equal to. What is a backslash equal again? Optional. Whatever is prior to this is optional. So that means the entire fractional part is optional. If you just want to say 5, it's cool. If you say 5 dot, it is okay. If you say 5.2755, that's okay too. Is that okay? Okay, so let's take a look at what else is following this. So whatever is following this is also starting with a backslash open paren, backslash close paren, and then backslash equal to, which means this entire thing, let me just use a mouse pointer to highlight that portion. So that means this entire portion is optional. You can have 0 or 1 occurrence of whatever is specified here. And that part has to do with the exponent portion of the scientific notation. In other words, if you want to specify pi as just 3.14, that's okay. It meets the requirement of this format already. On the other hand, if you want to specify the speed of light, okay, which is 2.97 e, what is the exponent of per second on it? Sorry? 23?
23?
No, it's like 8.
Yeah, I thought it was like.
Okay.
But it's meters, so that can't be right.
It's either 8 kilometers or 8 meters.
Kilometers, that makes sense.
Okay, so that would be the, but then you will want to have a scientific notation in that case. So that part is optional. So the optional part starts with a d. That e is mandatory. If you want to specify the exponent, it must start with a lowercase e. That is not optional. Within the optional part, it is not. And then followed by an optional sign, because it is either a plus or minus, but it is optional. And then followed by a single digit, but now we have a new thing. Backslash plus means one or more of the previous thing. So the exponent has to be e, optional sign, and at least one base 10 digit. But it can be more than that. Is that okay? So that whole thing, so this entire thing is basically the regular expression to define what we consider, or what this particular discussion consider as a valid base 10 scientific notation. Are we doing okay so far with this? Okay. So the first part of your, if you want to do a homework assignment, this is the optional part again, it's not going to be graded, is to write a program. If I give you a string, okay, I want you to parse that string first to make sure that it is syntactically correct. But the second thing is to separate the mantissa from the exponent in base 10. Okay, so we're not converting to base 2 yet. I just want to pull apart the base 10 scientific notation and say, this is the part of the mantissa, this is the part that specifies what power of 10 we are specifying as the magnitude. Okay, so that's one little exercise that I want you guys to do. It's not going to be graded, so it's optional, but I will give you my solution to this part. Once you have done this part, then the fun really begins. So once you have done the parsing part, then what we'll do is we're going to convert it. And let me look at the time. We got 3 minutes. I do want to give you the roadmap of what we're going to do in the next few classes, other than the exam and also the practice exam itself. So what we're going to do is we want to convert the representation. This is what we start off with, okay? Because the string is in base 10. Okay, when you type something in your calculator, it is in base 10. So we have a mantissa that is in base 10, and we also have an exponent which is in base 10. So the quantity that your scientific notation is representing is this expression here. You have a sign, you have a mantissa in base 10, and then you also have an exponent in base 10. Which is fine, because that's how we represent values in the scientific notation. Ultimately, what we want is a base 2 representation that is also quote-unquote scientific notation. So we want to somehow convert this into the same sign. Sign doesn't change between the conversion. But we want to change the mantissa to a base 2 mantissa. But the most important part is, instead of specifying the magnitude as 10 to the power of something, we now want to specify the magnitude as 2 to the power of something. So we want to do this process. Okay? The rest of this module, if you look at the thumbnail, you can kind of get an idea of how much stuff we have gone through. About 1/2 of the material. So the rest of this module really talks about how to code your program, how to write some code to do this conversion. And the conversion process is not going to make use of floating point calculations. Does that make sense? If you want to do the conversion from string to floating point notation, but it requires floating point calculations, that just doesn't sound right to me. So the rest of this module is going to talk about the logic to do all that conversion but only using base 2 calculations. Basically, we're just using compare. There's some division, but not a whole lot. So the rest of this whole thing really just talks about, how do we start with a base 10 scientific notation? How do we convert into base 2 scientific notation? Because once we get to a base 2 scientific notation, the double precision format is really just pulling things from different parts and kind of concatenating all the components into one 64-bit chunk of stuff. Is that okay? So we have this ungraded assignment, which is just validating an input string and separating the parts. I want the base 10 mantissa, the base 10 exponent. Just have those two components separated. Is that okay? All right. So this module is not going to be in the exam because there's no way I can finish this by Wednesday. So the floating point representation is not going to be in the scope of exam 1. So exam 1 has everything up to but excluding double precision, but it will include comparison and signed representation. Yep.
Are you going to put the practice exam online?
Yeah. Yep, I will. All right. So we'll go ahead and go to the lab and take do the lab activity today, which has to do with your base floating point representation.
What do you have to do?